Okay, and as like I told you, infinity norm is exactly what we need. The maximal absolute value of this vector, of this difference. So our problem in the most short way may be formulated as minimize over alpha infinity norm of phi alpha minus h, and as we already told, this can be solved by a linear program. I only suggest you to think at home how to express this linear program in more convenient way. What we are used in linear programming, this is minimize some c transpose x. It's some general x. It's not related directly to what we have here. Sorry, we didn't have x yet. Here is alpha. Subject to ax greater or equal to b. So, and one can ask question if there is a solver, a program which knows to solve problems in this form. So it asks you only to provide vector c and matrix A and vector B. So one can, having all those numbers, can say what will be C, what will be A, and what will be B, and this question I leave you for your home consideration. Now, often people are interested in complex valued approximation of functions. For example, we have a complex function of a real variable, for example, h, and we would like to approximate it as a sum of some elementary functions, which are also complex. This will lead us, as we will see, to conic quadratic programming problem. To move on, so I just start with discrete time formulation, as you see, and to make our notation more easy, I will define this function of alpha as zt of alpha. This is a complex function of a real variable, vector variable. And so I just will rewrite my problem, so it will be minimum over alpha, maximum over t, z t of alpha, absolute value. Now, I am interested somehow to get rid of complex numbers, and it's possible to do it in a rather convenient way. Instead of complex number z, I will use two-dimensional vector. It's real and imaginary component. So I will define this ut. I will define number of these vectors, and each of them is two-dimensional vector with components real z, zt, and imaginary zt. Okay, and so I have an absolute value of complex number. It's square root of sum of squares, its real and imaginary components. It will be exactly the true norm of ut. So absolute value zt is equal ut to norm. So I want to bring to minimum maximum of those values as functions of alpha. And I just write immediately the result. So we need to minimize tau subject to tau greater or equal ut second norm for t 1 to capital T. And this is my problem. Again, I wanted to maximize, to minimize maximal absolute value of z. Instead of, I told this should be maximum 2 norm of vector u of vectors ut. Each of them depend on alpha. Actually, it's better to write alpha also here inside. So it's u t of alpha. And of course, minimization over alpha and tau. Alpha is vector. So what we have here, optimization problem with linear objective function. And if you recognize second order constraint, because instead of this inequality, I can say that my vector u, t, and z just belong to Lorentz cone. If you remember definition of Lorentz cone of dimension 3. So we told that in Lorentz cone the last component should be larger than the second norm of vector of all previous components. Sorry, here is of course tau, not z. Okay, so actually this is already conic quadratic problem. We can try to write it in more convenient for us form, which likes like to minimize linear function of our vector of variables, which will be alpha tau, in the way that all this vector belongs to some cone, to one cone. And this may be done if we consider the following cone. Let's define a cone K, in which space we will define it. In R. So we have many cones. We have actually T cones. And those three T cones, so I have 3 capital T variables and I have t cones. So they will form large, I will call it super cone, which properties it will have. If let me these three variables define as Vt. Okay, Vt is a three-dimensional vector, and then I will define my vector V in this space R3T in this following way. It will be V1. V1 is a vector three-dimensional, and then V2, and then Vt is equal. I just will open this. U1 tau. This U1 is a two-dimensional vector and tau is one-dimensional. All this of dimension 3, and U2 tau and U capital T tau. Okay, and I want to build such a cone that my problem will look in type minimize, say, like is here, tau alpha tau, subject to this vector V of alpha belongs to this cone K. So how can I define this cone? So my first three component will belong to a Lorentz cone. My second three component will belong to another Lorentz cone, and so on. So I can define this cone K as a so-called direct product of T Lorentz cones. So L3 by L3 and so on by L3 T times. And say that some vector belongs to K, it's the same to say that first three components of this vector belongs to the first Lorentz cone, the second three to the second Lorentz cone, and so on. This is a definition of direct product of several sets. Okay. Actually, we almost defined our problem, except of the part that we have a vector alpha, and we want values alpha also to have a complex values. We want alphas to have a complex values. So again, if we want, if we like to have an entire optimization problem defined in real numbers, so what one can do, one can define our all vectors of variables. What are our variables? This is tau and alpha, and instead of every complex alpha, I will write its real and imaginary component. So I can define vector x in the following way. It will be tau and then real of alpha 1, imaginary of alpha 1, and so on, real of alpha n, imaginary of alpha n. Now I did all necessary preparations to write my problem really in conic quadratic form. So let me remove here. You remember what was our U. So I just can write that my problem is minimum some C transpose X subject to say AX minus B greater less or equal 0. It's mistake here. Greater or equal 0 in the sense of K. It means AX minus B belongs to the con K. So again, vector X is written here. How can we get this matrix A? So we have this V of alpha belongs to K. And let's see what is this V of alpha. Is U1 tau, U2 tau, and so on. And in what depends on alpha is U1, U2, and so on. Depends on alpha. How it depends on alpha? This is a linear function of alpha, and I just remind you what I just erased, that U was real Z UT, real ZT and imaginary ZT. Okay? So now you have all components. You have definition of X and you have a definition of linear function of X which belongs to K. You have all components to write explicitly for this conic program what will be vector C and what will be matrix A and what will be B. And of course the elements will depend on components of our original problem, and I leave it to you as your homework. Hello, this is lecture number 17 of our optimization course, and today we consider ways to convert different problems to semi-definite programming. The basis for conversion of many problems to the semi-definite programming is given by Lemma of Schur complement. So what the lemma says, if we have a symmetric block matrix, here are blocks P, Q transpose, Q, R, such that this bottom right block is positive definite. Then the matrix A is positive definite if and only if this expression is positive definite, and the same for semi-definiteness. This is very, very useful lemma in semi-definite programming, but also in many other areas of algebra. And the proof is not very difficult. Proof. So we want to check whether matrix is positive definite. How can we check? We can go by definition. For some matrix, I don't know, W, just one checks X transpose WX should be greater than 0 for any non-zero X. Because our matrix is blocked, let me rewrite it, Q transpose QR. We also will split our vector X in two parts. So we will, instead of X, we will try U and V. We will write U and V. Those are vectors, one under other. And here I can write U transpose V transpose. And this should be greater or equal to 0 for any U and V. But we can also simplify this problem. If it's greater or equal to 0 for any U and V, if we fix U, for example, and say that infimum over all possible V should be also greater than 0, we also will be right. So I will write here infimum over V. Okay. Actually, what is written here is a quadratic function. You can open parentheses and write explicitly how it looks as a function of V. About U, you are thinking as constant. So this should be correct for any U. And try to minimize over V. This is quadratic function, and we know to write optimality condition, which gradient with respect to V should be 0, and so on. And then I just will write expression. This infimum will be U transpose P minus Q transpose R inverse Q multiplied by U. And this will work, of course, if R is a positive definite matrix. So R should be greater than 0, positive definite. Then it would be the same, like say that this expression should be greater or equal to 0 for any U, or the same is to say that this matrix should be positive definite. Actually, I wrote larger or equal at every place, so I proved for positive semi-definiteness, but for positive definiteness it's just parallel. Should be positive semi-definite. So in order to satisfy this for every U, and this is what we have, I only leave for your homework to show this equivalence. just open it as quadratic function of V and write optimality condition. Now, first problem which we will show its conversion to semi-definite programming will be the following one: minimum of maximal eigenvalue. And so it's formulated in this way. Suppose that we have a matrix which depends on vector x, Euclidean vector, in the way that we are used in semi-definite programming. Ax, say, minus b, where I will open this operator A, is just sum over I, xi, ai, minus b, where ai and b and I and B symmetric matrices. And often in engineering and control and so on, people want to minimize, I would write symbolically lambda max of A, where A is function of x. Minimize over x. So it can depends some stability of control system and so on. Depend on this maximal eigenvalue, whether it's larger than 1 or smaller than 1 and so on. How can we deal with this problem? So suppose that matrix A has eigenvalues. I will put them into diagonal matrix, lambda 1 till lambda m. And I can write my problem minimize lambda max as minimize some scalar t. Let me write here all variables. Subject to lambda max from A of x, subject to t larger than lambda max. So again, I minimize in t and x. Okay. How can I open this constraint? I can say that t larger or equal lambda 1, t larger or equal lambda m. Okay? Yes, if it's larger lambda max, it must be larger or equal than any of lambda. And even better, I will write it instead t minus lambda 1 is greater or equal to 0, and so on, t minus lambda m greater or equal to 0. Let's now write the matrix of this form. T multiplied by identity matrix minus A. And I will ask you, what are the eigenvalues of this matrix? And I will write answer and you will think at home why it is correct. So the eigenvalues will be just t minus lambda 1 and so on, t minus lambda n. This is like diagonal matrix. Okay. So saying that all those eigenvalues of the matrix are non-negative, it's the same like say that this matrix is positive semi-definite. In this way I go to my final formulation, minimize t of course over t and x, subject to t identity minus a of x positive semi-definite. And this is semi-definite problem for this long variable, long vector t and x. And we will learn very soon that there are efficient methods to solve it. So we know numerical approach to minimize maximal eigenvalue of a matrix which depends linearly on x. Related topic to the minimizing of maximal eigenvalue is so-called linear matrix approximation, which also is a very typical problem in scientific computing and engineering. So suppose we have a matrix A0 and we want to approximate it as a weighted sum of some given maybe simple matrices or matrices with nice properties A1 to An. So we write as A0 is approximately x1 by A1 plus xn by An. x1, xn till xn are numbers, scalars. And so we want to minimize error of this approximation. And let's define this error as a of x is approximation minus a0. So it's sum xi ai, I from 1 to n minus a0. And what one would like to minimize norm of this error matrix, and again norm may be very different, so we would like now to minimize its operator norm. Operator norm of a matrix, it's maximum elongation of the vector of all possible vectors, relative elongation, which obtained, it's like maximum over u a u, usual Euclidean norm, but u should be restricted to unit both. For example, Euclidean norm of u is less than equal to 1. That's one of definitions. So we would like to minimize this property of error matrix. It's known from linear algebra that norm of matrix, operator norm of matrix, is the same as maximal so-called singular value of A if somebody knows singular value decomposition. If not, I will write it immediately that its maximal eigenvalue, lambda max, of the matrix A transpose A. And one should take square root of this maximal eigenvalue. I might say that I leave for your homework to try to derive it, and if you cannot, just find in linear algebra books the proof of this fact. It's very useful and very important. Okay, so actually our problem is to minimize over X lambda max of A transpose A transpose A. I skip here argument. And actually we already know how one can minimize maximal eigenvalue of some matrix. It's minimal T subject to Ti minus A transpose A greater equal to 0. Actually, for convenience, it would be better for me to write here T squared. And one can easily to see that it's the same. I could write also T squared here, and that will be just the same problem, just using different variable. And minimize T is the same like minimize T squared, but just you need one additional constraint T greater equal to 0. Okay. And then we can use so this problem is still not very nice. It's not a classical semi-definite programming problem, because the expression under constraint, first of all, here positive definiteness, it's matrix constraint. The expression under constraint is not linear, and we are used, and it's better for numerical computation to have here linear expression. And I just will write you how it can be expressed through Schur complement, and you will check me whether I'm right. So it's the same like minimize T subject to the following matrix should be positive definite Ti A transpose of X, here A of X, and here Ti. So this should be greater or equal to 0, and as I told, T also should be greater. Actually, T should be greater than 0 in order Schur complement to be working. Actually, you know It's a good home task to check whether using Schur complement lemma those two problems are equivalent. The only thing I don't need actually this inequality t larger equal or even larger than 0, and I explain you why. If I found some matrix, all this matrix which is positive semi-definite, and it's not 0, it's something other than 0, because if it's 0, it means that a of x is 0, and then I just minimized with 0 error, and I have no problems remained. Suppose that it's not 0, then the trace of the matrix for any matrix, say W, trace of W is sum of lambda I of W. This is very known property. So if W is positive semi-definite and non-zero, then sum of eigenvalue would be greater than 0. Then let's see what is trace of this matrix. If we called it W, then trace of W is equal, here is identity m times, m is the size of matrix. I don't remember where I wrote it anywhere. It's actually the small size of A. Okay. Suppose m is the small size of A, so it's 2m. It's t multiplied by 2m. 2m is 2m y's. And this is greater than 0 if w non-zero. If w non-zero and w greater equal to 0 satisfying this constraint, so automatically we'll get t greater than 0. And if a result of optimization be good, w equal to 0, actually we have nothing to do, because we know that we got optimal solution, because a should be 0. So only when w is non-zero, we have to show equivalence between those two problems, and this you will try to do at home using Schur complement lemma. Now we will learn how to express several known optimization problems via semi-definite programming. This link is often of theoretical value, because for computations, for example, linear programming solvers are more efficient than semi-definite programming, but for theoretical point of view, it's important to understand that those problems are connected. Namely, linear programming is a particular case of semi-definite programming. To understand this, we will write linear program in the following form: minimize linear objective, subject to linear inequality constraints. So, to convert it to semi-definite program, we will do a very simple trick. We will form a diagonal matrix, putting those entries on diagonal. And so this matrix actually linearly depends on X. So this is a semi-definite problem. And the constraint of diagonal matrix to be positive semi-definite, it's equivalent to say that diagonal entries should be greater or equal to 0. So those two problems are equivalent. Also, conic quadratic program can be expressed by semi-definite programming. Let's see this. Here's an example of conic quadratic program. We minimize the linear objective function subject to conic constraint, conic quadratic constraint. So we have this vector u, v. U is a vector actually, and v is a scalar. This forms long vector. It should belong to Lorentz cone, mean norm 2 of u less or equal than v. And here are expressions for u and v. And the claim is that this semi-definite program is equivalent to conic quadratic one, and we will show this equivalence again using Schur complement lemma. So how can we use it? Okay, I wrote it offline. Here is what we have by Schur complement theorem for this matrix. Okay, so this is our first block, and then u transpose by this block inverse, u transpose by this block inverse by u greater or equal to 0. We only have to say that this is positive definite. It's the same to say that v greater than 0, and this really will take place if this matrix is non-zero and positive semi-definite, because v defines trace of this matrix. And if matrix is positive semi-definite and non-zero, the trace is strictly larger than 0, so v is larger than 0. Okay, let's get back to this expression. Actually, one can see that this is like, right, remember that v is a number, v inverse u transpose u. If you will do manipulation with diagonal matrix, you will see that this is really the case. And let's so this expression should be greater or equal to 0. Let's multiply by v. Multiplying by v, we get v squared minus u transpose u greater equal to 0. Okay, this is the same. We take put in other side and take square root, you will see this inequality. So we showed that those problems are equivalent. Okay. Now we get to the point where we will learn how to solve conic programming problems numerically. And the basic approach is this barrier method. We already learned barrier method in nonlinear programming, and the general idea is very similar. So suppose we have a problem of conic programming of this kind, and suppose there exists strictly feasible x. How can I express it? So exists x strictly feasible, mean which satisfy ax minus b really greater than 0 in the sense of con, and this record means that point x is inside, strictly inside the con. I mean there is a finite ball around x which also all belongs to the con. So then we can define a barrier function which will have some moderate value inside of con and grow to infinity towards boundary of the con. So we will define barrier, some function phi, which acts from the points in the con to real axis k to r, and the property, as I told, that the limit of the barrier, limit of phi of u, when u goes to boundary, I will denote this in this way. And from inside, so u should belong to k, u belongs to k. So this limit should be infinity. The only correction to what I told before, x strictly feasible, then ax minus b, I can denote this like u, it belongs to the con. So the ball is not around x, around u, which gives points belonging to the con. And now we can define barrier aggregate. It's very similar to penalty aggregate for nonlinear programming. So it's objective function plus barrier for which forces this value ax minus b really belong to the con. And what will happen when mu become very large? So the value of barrier inside the con, it was some number, so it will go to 0, but still it will go to infinity towards boundary. So I can say that if infinity of x is C transpose X when AX minus B strictly less than 0 in conic. In conic sense, in this point is inside the cone, and infinity otherwise. So, and it's quite understandable that if one would find minimum of this ideal aggregate, then it will be solution of the problem. So minimum of f infinity, minimum in x, f infinity of x is just optimal value for the original problem, which we denote as f star. And of course, the algorithm, numerical algorithm, would be to find the minimum of this aggregate for moderate mu with some reasonable accuracy, and then say multiply mu by 2 or by 10, then find minimum again, and continue, say, till mu will achieve in practice, say, value of 10 to the 5 or 10 to the 6. And then you will get a solution of your conic program with reasonable numerical accuracy. And here I just present examples of barriers for 3 basic cons which we use in conic programming. So for Rm plus, case of linear programming, we already know that just take logs of your constraints. And this was written here. For Lorentz cone or second order cone or quadratic cone, you remember that um, the last entry of the vector, should be greater than second norm of other entries taken as vector. So um squared should be greater or equal than sum of squares of other entries. So we just take log of this difference, and one can show that this is nice convex function which has this have properties which is goes actually to infinity on boundary, and we actually see it from here. When the point approaches boundary, then this approaches 0, so it goes to infinity. And the third case is for semi-definite programming, we need some barrier for positive semi-definiteness of matrix, and the good barrier is minus log det of this matrix. And how can one understand why this barrier is good? Because actually log det of matrix, let's take some abstract matrix A, so log det of A if you remember, probably determinant of matrix is the same as determinant of its determinant of diagonal matrix which with eigenvalues on diagonal. How can... Well, let me remind you a bit of linear algebra. So suppose A is S minus 1 lambda S. So we have a eigenvalue decomposition of A. Then what is the determinant of A? A is we know that determinant of product is product of determinants, and also determinant of inverse is 1 over determinant of original matrix. And if you take this into account, so it will be determinant of S 1 over minus 1, determinant of lambda multiplied by determinant of S. So this will cancel. And determinant of diagonal matrix is just a product of its entries, so it's product of lambda I from 1 to m. So log det of A, you have minus log det of A of matrix. So minus log det of A is just log of product. This is minus sum of log minus sum of log of lambda I from 1 to m. And this formula shows us that if we started from some point where matrix A is positive definite, so all eigenvalues are positive, this function, this barrier will prevent us from moving to the area where one of eigenvalue become negative, because when we're moving to this area, we should cross the point when it becomes 0, and then this log, minus log will explode to infinity. So this really shows that this is a reasonable barrier. And actually this is nice, smooth and convex function. It's rather good for optimization. And now we will show how to treat it, how to compute its gradient and so on. Now, in order to continue, for example, one wants to solve a numerically semi-definite programming problem and needs to get gradients, for example, of barrier, which includes log det of some matrix. We need to get back to the basics of matrix analysis, and I will remind you what is matrix function. So suppose that we have a usual scalar function of one variable, for example phi of t, which has a polynomial expansion, some I from 0 maybe to infinity, or maybe finite representation, ci t to the power I. Then we will define a matrix function phi of matrix A should be a square matrix, just as a sum, just the same polynomial from the matrix A. Sum I from 0 to infinity, ci a to the power I. what is power of matrix? It's just to multiply matrix by itself I times. And if somebody has this expansion, for example, the most popular is matrix exponents. So if you have exponent and you have a Taylor expansion, you can define what will be exponent from matrix. But one can use the same principles, say, to define what is sinus of matrix and so on. But still, this computation is heavy because you need to multiply matrix, which become as m cube complexity when m is the size of matrix. But if one knows to do eigenvalue decomposition of matrix, this computation become much easier. So that's why we will need to remember, I will remind you, what is eigenvalue decomposition. And of course, all of you remember definition of eigenvalue and eigenvectors. So if I have matrix A and multiply it by some vector S, and this is equivalent as multiplying S by some number, I mean it doesn't change direction, it only changes length and probably changes direction to opposite, so lambda maybe not only positive, then S is an eigenvector. What I can do next is say, suppose that matrix A is so good that it has m different eigenvectors, where m is the dimension of my space, size of matrix. Then what I will do, I will put all those eigenvectors to the column of a matrix, which I will call capital S. And because of this relation is correct for every column, one can see, and I suggest you to do this exercise yourself, that I can define a diagonal matrix lambda with entries. Now I have m vectors, so let me denote it as Si, and lambda I will be corresponding eigenvalue. So I put on diagonal eigenvalues lambda I and put Si as columns of this matrix. And to say this, the same as to say this. And I suggest you to check it. Okay, S is S lambda. And what we will suppose that we have m linearly independent eigenvectors. This means that square matrix S is invertible. So let me multiply this equality by S inverse from the left, and from the right. It's better to me now to do it from the right. So I will get A, so S by S inverse will be identity, will cancel. S lambda S inverse. You should note for yourself that this is by multiplication by S inverse of this equality. Okay. Now you see that for matrix function I need powers of matrix A. Let's see what will be A square in this case. So A square. I just substitute S lambda S inverse, again S lambda S inverse. So it's A by A. Okay, this will cancel. Lambda by lambda. Multiply diagonal matrix is very easy. It's element-wise multiplications of it and entries. So this will be S lambda squared S inverse. And I can continue such manipulation for any degree of matrix A. So I will get that A to the power n is just S lambda to the power n S inverse. Now my computation is much easier. And what will be phi of A? I will write your result and then we will see it together whether it's right. It's S phi of lambda S inverse. Is it correct? I will substitute the sum, and then instead of degrees I will write this, and then S and S inverse I take out of parentheses and get the same expansion only by diagonal matrix lambda inside. And I can even open, what does it mean, phi of lambda? It's taking this expansion of every diagonal matrix. So phi of lambda is actually a diagonal matrix which with my scalar function, original scalar function, phi of lambda 1, phi of lambda n. Here are zeros. Again, so I had an expansion of lambda. I have a series with respect to matrix lambda. This means that I have the same series of every entry, and then back by this formula I get that every entry actually will be a scalar function of lambda. The only thing I want to say in addition, if A is symmetric matrix, all this will be the same. The only property of symmetric matrix is that its eigenvectors are orthogonal, and I can normalize them, and for orthogonal matrix its inverse, it's just its transpose, because you compute S transpose S, and all mutual scalar products of eigenvectors with other eigenvectors are zeros, except of one with itself. So for symmetric matrix, matrix A, S inverse is equal to S transpose, and of course phi of A will be just S phi of lambda S transpose. And there is one more thing I will need to take trace of matrix function. So matrix function is a matrix which depends on my matrix A. Trace is a number. So I want to express trace somehow it's a function of eigenvalues. So let me substitute trace of phi of A. We told phi of A is S, phi of lambda S inverse. And what I can do now, it's known that under trace there is a commutativity of the matrices. Trace AB is equal to trace BA, despite of there is no commutativity of usual matrix multiplication. AB is not equal to BA, but trace AB is equal to trace BA, and I suggest it for you to check yourself. And so I can move under trace this matrix to here. So it's by commutativity of trace. You will write trace as inverse S phi of lambda, and of course this is identity matrix. So I get trace of phi of lambda. Trace is sum of diagonal entries. It's actually sum I from 1 to m phi lambda I. So very useful formula, and we will use it in order to get gradient of log det in semi-definite programming. What we will also need is a gradient of trace of matrix function. And the claim is that in order to compute gradient of trace phi of A, you just take a scalar function phi prime derivative of phi and apply it to matrix A and take transpose. We will not get full proof of this. It's a bit long expression. I just will show you a particular example, but the example is rather general to derive from it full proof. So let phi of t is just, say, t cube. So in this case, phi prime of t, of course, it's 3t squared. Okay? So, and denote this trace of phi of A like f of A. So f of A is trace, I write again, phi of A is trace A cube, trace of A by A by A. This is usual matrix multiplication. Now, we already know a standard way to derive gradient of any function. We should see what is the differential of a function when we make some increment to the argument, and then we say the differential of the function is scalar product of gradient with differential of argument. So in this expression we will try to see scalar product. This immediately will give us gradient. So let's see what is df of A. df of A. I would say it as following way. This is trace. If I have my argument in several places, then to get a full differential, I can just to think about argument of changing in one place and being fixed in other places, then in second, then in third, and to put it into sum. So it will be trace dA multiplied by A plus trace A multiplied by dA by A, and plus trace A dA. But the nice thing about trace, like we told, there is a commutativity. So, for example, if I want to put dA in, say, into first place in the trace, I can think that here, for example, trace is product of this matrix A, and this is other matrix. So I just change them by places. It means that if there are many places under many matrices under trace, I can do circular shift of this expression. And what I finally get is just 3 times trace dA, and instead of A by A, I will write A squared. Okay. Let me continue here. And what I have, that this is, I should remind you before I continue definition of inner product of two matrices. So if I have two matrices, A and B, so I define the inner product like trace A transpose B, or the same as trace B transpose A. And it's actually the same as put A and B into long vectors and to make a scalar product of these two long vectors. It's sum of element-wise multiplications, element-wise products, pairwise products of elements of A and B. Now I am ready to continue. So actually, what I have here, if I continue from here, I have a scalar product of dA with matrix 3 A squared transpose. Yes, transpose because this definition. And okay, so we compare with dF is inner product of dA with gradient of f. So this is gradient. Gradient of f is 3 A squared transpose. But if I compute phi prime of A, this exactly will be 3A squared, and transpose is here. So we got, at least in this case, we got that this formula is correct. This formula is correct. And of course you understand that this is general idea for any polynomial expression. I just didn't want to write long formula, and you can easily to accomplish yourself for any polynomial function phi of t. Now we are ready to get back to our main goal, to compute gradient of barrier for semi-definite program, log that a. I skip minus here. So here is our function of matrix. Okay, scalar function. Put attention. So what is written here, it's log of product of eigenvalues, or sum of log of eigenvalues, or I from 1 to m. And if you remember what was trace of matrix function, it's sum of functions of eigenvalues. So what is written here is just trace of log of a. Okay, and we wanted gradient, so we know what is the gradient of matrix function. So our scalar function phi of t is just log t. What is its derivative? Phi prime of t. Phi prime of t is 1 over t, or t inverse, I can write. So gradient of f of a will be phi prime of a transpose a inverse transpose. This is the formula we will need. Sometimes people use short notation as a minus t to take inverse and to take transpose. And for our goal, this formula is even more general than we need, because we will work with symmetric matrices, so we will not need transpose. So we have our barrier as a function of a, and have its gradient with respect to a. But actually in semi-definite programming we will write it as a function of x. We have a linear operator which maps from x to a. And to get gradient with respect to x, we again will try to get some scalar product mapping dx to d phi. So we already have gradient with respect to a. So d phi is a scalar product of gradient with respect to a by dA. And now we will just substitute dA, which we can obtain from here. So gradient with respect to a of phi multiplied a calligraphic dx, because this is a linear operator, it's differential, and we of course want to separate x in scalar product, and we can move a to the left side of the product using its conjugate. So it's adjoint phi. So it's A adjoint multiplied by gradient of, with respect to A. And comparing with the basic formula of gradient of differential, so here should be a gradient in this place. So gradient with respect to x of phi of a minus ax minus b is just a adjoint multiplied by gradient with respect to a of this expression. So we know to compute gradient of the barrier, and we can apply any gradient based optimization methods to minimize it and to get solution of semi-definite programming problem. Of course, usually one applies Newton method, and for this you need to compute Hessian. It's a bit out of scope of our course, and this is the last lecture, and we finished actually the third part of the course, Conic programming, and maybe several lectures will come in the future. Thank you very much. And derivative, if it's 0 at the origin, it must be 0 for negative values as well. So I will write lambda star is 0, and gi is less than 0, and this means that phi prime of gi must be 0, and this is exactly lambda I star. Okay. Therefore, second. Sorry, I wrote this formula offline. So therefore we have that gradient of augmented